Hello, everyone from wherever you are in the world. Welcome to today's webinar. My name is Tepiso Morabe, and I am going to be your moderator for today's webinar. Okay. To begin with, please take note of the notifications and sound slide that is up on your screen. This is so that you're able to minimize any sounds that might come through. Please note you're able to turn them on and off as you please. And then please also take note of the Q&A tab that is in the top ribbon of your screen. That's where you're able to make any comments. You can also utilize the chat box should you have any questions regarding today's webinar. We will have a post session Q&A at the end. Please make sure to note your questions down. If they're related to the Engineering College of Technology, I'll make sure to answer them. However, if they are relating to today's presentation, I will allow Steve to answer those questions at the end. Okay, some common questions for you. Please note you will receive both a copy of the slides as well as the recording. They will be sent to you in your mailbox. If you can't find them in your normal mailbox rather, please make note to check your junk, spam, and promotional folders. They might land there if not in your normal mailbox. You'll also have the opportunity to request for a free digital certificate of attendance. I'm going to leave the code and the QR code rather and link for you guys to request for the certificate. Please be mindful that you write your names as you'd like them to appear on the certificate of attendance so that you don't have any issues on that. Okay, a little bit about ECT, that is the Engineering College of Technology. They are engineering specialists, and ECT is affiliated to well-established Engineering Institute of Technology. They offer industry-driven programs, and the programs that we offer are designed by industry experts, ensuring that you graduate with cutting-edge skills that are valued by employers. We also offer world-class accredited education programs. ECT is registered by the UK government for students, the Office of Students Requirements, and you can for sure check those standards with them if you have any questions. But again, you are more than welcome to ask our course advisors. They'll be happy to assist with any questions you might have, as well as provide you with information that you might need regarding the programs. We also have industry experienced lectures and instructors. And lastly, we offer a unique delivery model. All the programs that we have on offer can be studied 100% online. All you need is a good working laptop as well as internet connection, and you'll be able to study with us regardless of where you are in the world. Okay, now for some rules, please, some housekeeping rules. Event conduct, please make sure to keep the discussion lawful and respectful. Let's follow the guidelines that I've provided you guys. Do not share any illegal or abusive content, and the recording is not permitted. You're not permitted to record unless we have authorized it. Because we'll be sharing this recording with you, you can just check your emails. It will be sent within 2 business days. And then lastly, breaches may also lead to removal as well as referral under ECT policies. Okay, there we are. Today's program, or rather webinar, is going to be practical process control and loop tuning. And your presenter for the day is going to be Dr. Steve Mackay. He'll be the one taking you through the presentation. Steve, are you all ready to share your slides with us?
Yes, I just want to check, Chippy. So I must upload them, the slides you're saying.
Yeah, so you're going to have to share right next to the leave.
Oh,
Right
okay, okay.
yeah,
So I'll just
you
share
share
them.
from
Okay.
there.
So I'll just run them.
Yes.
Okay, sorry.
So let me stop sharing.
I'm a bit off.
No, you're not, but you click on share and then you look under PowerPoint Live. So please
Yeah,
do that.
I've just got it there now. So I'm going into share. Hopefully, okay, share. There we go. And PowerPoint.
Yeah, are you sharing? You're going to share from your screen.
Yeah, that's right. I'm just looking for the share and the screen. So I go screen, do I?
Yeah, you can share your screen. If you have the presentation open on the other screen, then definitely do that.
Is it under window or is it under?
So there's two screens, the first one, and then the second one where you would have had the presentation open. Did you open the presentation, Steve?
Yeah, my presentation's open. Yeah,
Okay,
got it.
so you should share from there. Or tell me, under PowerPoint Live, can you see the presentation? It should say ECT, the name of the present. It should say ECT Essentials of Process.
Sorry about this, everyone. So in the Teams, I've got to share. It says share content. That's where I am, isn't it?
Okay,
Stand
so
out
yes,
side by
so
side.
there's screen and then there's two screens on there. Do you see
Yeah, that's
that?
right. It's got screen. I've got screen. Yep.
Yeah, please share the screen where the presentation is open. It should appear there.
You're sharing your screen right now.
Yeah, I can see your screen. However, I am seeing
There's
three.
nothing. There's nothing coming up.
Okay, open the
Uh,
presentation from there, please, so
that
that we're able to see.
presentation's open. Can you see
Okay,
it?
I cannot see it, Steve. However, Britt is getting someone to assist you, so Tech will be with you shortly.
Doesn't share. So that's the PowerPoint.
Mm-hmm. Or what we can do right now is that you can begin with the presentation on my end, and then you can just tell me when to move it. And once you have
Yeah, it's
someone who's
probably the
assisted
quickest.
you,
Yeah.
we will
Which one?
reshare from
No,
your
that's the one I
side.
went to. Screen. Sorry. Where?
Like Caroline. Okay, great.
Share. Oh, okay. Okay, I'm almost there. Anonymous. Okay. Is that sharing something? Can you see something? Security alert. Can you see this, Chippy?
Yes, Steve, I can actually see this.
Okay, good. Excellent. Okay. This is very complicated though.
Okay, all good.
Okay, to get the chat, oh God. Okay. Okay, everyone, are we all on? Where did I get the chat, the actual texting in the boxes, Chippy? Hello, everyone. Can you hear me? Can you please text in the
Loud and
box?
clear. Loud and clear,
Okay,
Steve. We can
but
hear
can
you.
you? But I just can't get the texting. The
I believe because it's a slideshow, that's why, perhaps.
okay, okay.
Do you
Okay,
perhaps want to
everyone.
do it?
Yeah, it's probably going to be better if we do it from you, because I need to talk to people, and the only way to
Mm-hmm.
do it is with texting. So it's
Okay.
not going to work this way. So perhaps the best thing is you just, I'll tell you to change the slides, and then we'll go from that
Okay.
perspective. I'll just
I'll do
kill
that,
this off.
Steve.
Yeah, it's probably going to be quicker that way. Let
Sure.
me just kill all this here. Sorry about this, everyone. Can you all see my? Can you all see my? You can all see my slides. Hopefully, Chippy, can you pull them up? And I'll
I
just
am uploading
just
as we speak.
okay. Thanks so much. And we can then text chat. Excellent. Sorry about that, everyone. My apologies. We had a little bit of there's a Microsoft issue with Teams, and it's a little bit hard to do the recording. So we were trying to get around that, but it's not going to work. So this is the best way forward. So thank you, Cheppy, for stepping into the breach. Dear friends, as they say from Shakespeare, dear friends, into the breach for England and King Harry. So apologies for that, everyone. Okay, so what I'm going to do today is I'm going to talk a bit about process control and loop tuning. And I'm also going to take a little bit of a chance, and I'm going to run one of our labs, but we'll get to that in a tick. So the first point to make is that this is not an advanced presentation. This is purely very basic, but it's going to give you the background to process control as I see it. And this approach to process control was given to me by an extremely knowledgeable guy. Unfortunately, he died of motor neuron disease, Wolfgang Altman, an incredible guy who's a Honeywell extraordinary engineer, and he taught me everything about process control, oh, so long ago, but extremely knowledgeable. And he said, all that stuff you learned at university, mate, just forget about it. We're going to talk about process control as it's done in the real world. Now, all I want to do with this presentation, it's 45 minutes, is give you a little bit of insight into the background for process control. So if you've been tuning loops all day and you are a guru in loop tuning, don't waste your time on my presentation. You won't learn much. But if you want to get a bit of background to process control, loop tuning, and the theory behind it, then this is the presentation for you. So please type your feedback into the box. The first question I want to ask you is, what are your titles? What are your titles? What's your job title? Job title. Just text it into the box. Is it a dog washer, chief engineer, car salesman, electrical engineer, technician, blah, blah, blah. Just put down there, SCADA engineer. Brilliant. Thank you very much. Offshore installation manager, retired. Oh, I'm sorry to hear that, Andre. Probably having a good time, relaxing. Mechanical engineer, project development manager. Brilliant. So we've got a very eclectic bunch of people, but that's fine. That's wonderful. Okay, so what we're going to do today is I'm going to quickly outline the objective, give you a quick introduction to process control, then talk about the concept of tuning of a loop. Then I want to move into the more arcane area of cascade loops, and then talk about dead time, which is killer number one for any PID, and then a wrap up. So that's where we go from this. Renewable energy, thank you, lecturers in project. You all got incredible background. Thank you very much for joining us today. And we've got Righteous Mawuli, Ayapath, student TTU. Brilliant. Thank you very much. Automation engineer, Gordon, and petroleum technician. Okay, fantastic. Okay, so if we can, I see I can change the slides here, Cheppy. It's quite interesting.
You can, Steve, however, it won't appear for our participants, so you
Oh,
need to
okay,
prompt
okay.
me when I should
Okay,
move, and
okay.
then
Can
I'll
you
do
move to the
so.
next slide? So
What
when I
slide are
scratch
you
my
on,
nose,
please?
agenda. Can you move
Okay,
to the next one? Thanks so much, Cheppy. Sorry to be a pest.
no worries at
I
all,
think we
Steve.
need to talk to Microsoft. Microsoft is a almost trillion, or a few $1 trillion business, and this is a little issue which is affecting them. But brilliant company, outstanding company. I'm not demeaning them at all, but we're trying to work around that. Okay, excellent. Okay, so Cheppy, if you can move to the next slide after agenda.
Sure.
Thank you very much. Okay, so obviously the topic today is practical introduction to how process control systems work, and a little bit of background to control loops, instrumentation, automation strategies. Okay, next one. Introduction to process control. Nice little picture there. And let's talk about the next one. Thank you. We've got a really eclectic bunch of people. Now, this is the magical slide, which gives you the whole process control model in a very abbreviated slide, but it gives you a pretty good idea about feedback control. So we're dealing with feedback control. Now, the first point to make is that you've got this little key thing there, which is basically your controller. So that's your PID controller. And the idea of that is this is the animal, the device, which we want to put in the P, I, and D constants. That's the critical thing. So that output, little OP there, shows you going into a process. And then the process you measure with a flow meter or a thermocouple, and then you feed that all the way back to PV. So that's your process variable. And you'll see the process variable, it's got a little sigma sign there. And that sigma basically means that you've got a set point PV and you get an error. So set point minus PV gives you the error. And that is what you feed back into your controller, the P. And the P is the animal which we want to spend 20 happy minutes thinking about today. This is what we're going to look at. Now, what we're trying to show you with this is you may have remembered, in fact, I had this experience yesterday. We had a band on the beach, and my son-in-law was playing in the band on the beach, which was quite interesting. And it was 40 degrees, and we had a storm. But there was a problem with the band in the sense that the music had a feedback loop. So when anyone spoke on the microphone, it went through the speakers and it came back into the microphone, and we had a feedback loop happening. And this is exactly what we're trying to show you with this loop controller and process. As you go from P output to the process, you get feedback. And that is something we've got to watch out for. So what we're trying to show you here with the black blobs, you see the little black blobs on the sinusoidal waveform? Unfortunately, I can't write on the slide, which is a bit of a pest. But we'll get around that. So what we've got here is a little black blob output from the controller. And as you can see, through the P controller, there's no problem. It goes straight from black to black. There's no what we call phase shift. As you go through the process, you can see the black blob is underneath, and then as it goes through the process, it comes out on the other side. The black part of the sinusoidal wave is inverted by 180 degrees. So the process is shifted by 180 degrees. So what happens when your gain, your loop gain, which is your controller, times by the process gain, this is like a multiplier, when that's greater than 1, and you've got a 180-degree phase shift, you get very bad things happening with your loop. Basically, you get a sinusoidal waveform which gradually grows and gets bigger and bigger and bigger. And that's a problem. So we need to avoid that situation. And this is the whole purpose of tuning a loop with the PID controller, which is the workhorse of loop tuners. So, Chippy, if you could just change to the next slide. If I scratch my nose, can you just change?
Sure.
Thanks.
We're on slide 14, right, Steve?
Yes, slide 14. Thanks.
Okay.
And then 15. You can't hear me. I'm sorry, Joshua. I am talking. Can you hear me now, Josh? Please hear me. I am talking. You haven't changed the slide, Chippy. It doesn't change it. Can you? Is it changed? Okay. Okay, slide 15 now. Okay, so what you've got now is, can you all see objectives of tuning? Just, okay, can you all? Yes, okay, great. So we've got to talk about what are the objectives of tuning. And now there are three parameters that we use for tuning. One is called the set point, which is the target value. The process variable, which is what you measure, could be a temperature, flow. And the third item is the output from the controller. So you may remember the controller has an output. That output is the result of the controller's setup. So I'm sorry I can't draw the slides here, but it's a bit frustrating for you, but we'll press on. So the first thing is over here with this diagram, you'll see that it's got a set point there, which is the step change, and then you'll see the process variable, which is the overshoot here. And the idea is that we've got to minimize the blue area. So the perfect controller, when you make a change to your output, it would go straight up with the square wave, and that will be as far as it goes. So that blue area is minimized. So the idea is that we minimize the integral of the error. The error is between the set point and the process variable. So that is the critical thing. And it's driven by the output of the controller. So the output from the controller is making a change to a valve or a variable speed drive. It's making a change to the process, and this is the result. We need to keep it there. So Chippy, if you can change to the next slide. Okay, and then obviously one of the challenges with any error is that you get positives and negatives. So we also want to minimize the amplitude of the error squared. So that red, again, we want to take it, square it, which means it's totally positive, and we want to make it as small as possible. Okay, next slide. And the next one is minimize wear and tear. So now you may say, well, what the hell does that mean? Can anyone tell me why we would want to minimize wear and tear? So just think about the output for the controller controlling a valve. Why would we minimize wear and tear? Just text in the box. Just put anything down. Hello. I think this is the reason why. Okay, Chippy, thank you very much, Chippy, for your comment there. Minimize operating costs. Yep, absolutely right. So basically, you want to minimize wear and tear because when you've got your valve, and if your controller is going up and down on that valve, saying, please go up a little bit, go down a bit, go up a bit, go down. The poor valve is going up and down, letting a little bit through and then a little bit down, going like that. You will damage that valve. So the idea is to have an output from the controller which is continuous and it doesn't jump around all the time. And that's really important. Otherwise, you will destroy the process that you're controlling, a valve or whatever. No overshoot at startup. Why would we want no overshoot at startup? That's not always the case, but you may want to set up your controller so you don't have overshoot at startup. Why would that be the case? Can you text in the box? Minimize continuous feedback, Righteous says. Well, think about a tank. And unfortunately, I can't scribble on the board, which I'd love to do. But if you've got a tank and it's full of water and you've got a target value of 90%, say, for example, I've got it 90% full, you don't want to have some overshoot so that the tank fills up to 110%. It's caustic soda, for example, or sulfuric acid, 110%, which means it's overflowing. So you want it to gradually go up from, say, 90% to 91%, not 90% to 120%, then down to 85%. So you want it to gradually go up. Or maybe you're pressurizing a cylinder, gas cylinder, Again, you don't want to have this massive overshoot. And so that's a really important thing with tuning. You may want a gradual movement. And then minimize effective known disturbances. That is always absolutely critical. And if you walk into any plant, you can be the best process control engineer in the world, but the people that know that plant are the operators, and they know every little tweak and twinge on that plant. So they will know, hey, there's a potential problem with that conveyor belt. It actually doesn't deliver the exact amount of ore. There's an overshoot in the bin. These are the problems that you have with this particular plant. So they may say, this is something you've got to watch out for. So you may say, that's another objective of a good tuned loop, is to minimize effective known disturbances. So that's quite critical. Okay, Chippy, the next slide, please. Okay, and Prince Chakira says minimize wear and tear so as to extend the lifespan of valuable assets. So I'm coming back to this loop control and process in my next discussion. So please bear in mind the little orange is the controller and the process there. Now the controller you'll see has only got P in it. P, and that means that I'm only looking at the proportional control. There are three parts of a PID control that we're going to be looking at: proportional, integral, and derivative. Proportional basically means take the error, P, set point minus PV, and multiply by a number. That's all it is. Integral says look at the error between process variable and set point and add that up. Add it up, integrate it, and then take a control action. And the derivative says look at the error and look at the change in the error. Derivative means taking the change. That's good old calculus. Okay, next slide, please, Chippy. Okay, so the first type of control which you always have is open loop tuning. So basically with open loop tuning, there's no automatic control. It's purely the output from the controller, you make a step change and you look at the results. So you can see here we've got the reaction curve for the process variable, and then we've got the slope. The slope is change in the process variable over time, so the x-axis is time, and the lag, can you see the lag there? It's actually when nothing's happening. Not quite, there's always a bit of happening, but the process variable takes a bit of time to change, and we call that the lag. And the way we do it is we take the line of the slope and we intersect with the x-axis. So you work out the tuning constants from that, and the tuning constants that you'll be working will be the P, I, and D from the N and L, slope and effective lag. They will give us the numbers we use. But we're not going to spend too much time on that. We're going to look at the normal closed loop tuning. So if you go to the next slide. So the most famous one is Ziegler-Nichols, and interesting enough, invented by a mechanical engineer in 1943, I think it was. And basically what their model was, 1943, that's a long, long time ago. They said, hey, what you do with a controller is you just increase the gain of the controller, just keep increasing it until you see oscillations. Now, no one in his right mind in any plant is going to allow you to have continuous oscillations. So we use a variation on this approach, and I will look at the variation, but it's interesting to see the theory behind it as to why it works. So what you do is you purely have proportional control, and we look for the phase shift. And then basically, once you get the oscillations, you will see things. Now, I'm going to try something. Can you go to the next slide, please, Chippy? Okay, so here we have it. So you can see oscillations here. Now, as I said, no one in his right mind is going to allow you to have oscillations in a plant. That's not going to happen, mate. But this gives you a useful approach to how it's done. Now, what I'm going to do, Chippy, I want to share my screen. Do you think it's going to be too ambitious?
Would rather try, Steve. You can try, you can
Now,
also
try.
send it. Yeah, you can absolutely try.
No,
You can
it's a
also send
screen.
it my
Okay, I'm going to
way.
try. I'm going to try it now. It's going to see what happens. Window and Electromeet Labs. Okay, here we are. Oops, connection error. Oh, God, what's it doing? Okay, can everyone see this? Chippy, can you see the screen coming up?
Yes, Steve, I can. However, yes, I can actually see that.
Can
I
you see
believe
it?
our
Excellent.
participants
Okay.
can as well.
Okay, thanks everyone. I'm sorry I won't be able to see your chats on the slide here, but here's a typical example of a controller which I've taken from our remote labs. And as Cheppy says, she can see it, so hopefully you can see it. Now, what we've got is a typical controller here. Now, I'm putting the controller into manual mode, and it's got output here. Set point, can you see at the bottom of the screen? Set point, output, tune, pause, zoom, exit. Now, pause obviously doesn't really happen in the real world, but it does happen here in my simulation. So this is a simulation from my lab. It's an incredible simulation put together by a very good friend of mine. He's unfortunately dead. All my friends seem to be dead these days. Anyway, he's was a professor of chemical engineering for University of Texas. An amazing man. Anyway, very clever. So he put together the simulation. He's got about 20 or 30 simulations we use for training, teaching our students. So in manual mode, if I make a change to my set point here, you can see I'm changing the set point. Chippy, can you see the set point changing up and down?
Yes, I can.
Okay. But you'll see there's nothing happening to the process variable in output because it's in manual mode. So can you just think about the controller there? Controller's in manual mode, and there's no, whenever I make a change to the set point, I want a target value of 90%, it just ignores me. It's only when I put it into automatic mode. So when we go to automatic mode, let's just make the set point close to PV. I'll put it into automatic mode. Now I'm automatic mode. Now, what I want to show you is when you tune, you've got tuning constants. So the gain, you've got reset, which is minutes per repeat derivative. And if I put in a value here, for example, let's make the derivative 0. Let's make the reset 1,000. Let's make it 300. I think we can put that in. No, maybe 300. No, it won't. Only lets me put in 100. Okay. So basically, all we've got is proportional control at the moment. Now, when I make a change to my set point, you can see the output changes, and then the process variable comes back. Doesn't do much. Now, the idea with tuning with the Ziegler-Nichols method is that you see the gain there. As I increase the gain, make it 2, for example, okay. Let's have a look what happens here. I make a change to my set point, and you see the output changes, the process variable changes, it settles down again. So basically, I have got my gain of my loop, the controller and the process, multiply is still less than 1. As I now increase the gain to something outrageous, let's increase the gain to say 9, which you'll never do. I've increased the gain to 8. Now, when I make a change, boom, can you see what happens there? The process variable is actually oscillating. It's actually oscillating in a fairly constant way. And can you see the output goes up and then the oscillations are dropping off? They're not sort of going berserk. As I increase the gain more, let's make it, say, 10, which is getting a bit extreme. If I make a change now, can you see the oscillations are getting worse? So basically, the key for this particular loop, it's a flow loop, we probably would have something like a gain of about 9 to get that perfect settling. So here, if I make a change, you'll probably find that's basically spot on. So that is a gain of about 1. And now I can use, as you can see, the process variables have sort of settled down, the constant cycling. And now that's the Ziegler-Nichols model at work. Obviously, the idea is that you're never going to be allowed to do that to your process, is to have that. But what you can do is have a damped approach. Now, it's beyond the discussion today because we're running out of time to go into the damped approach. But this to show you, this is how the Ziegler-Nichols model works with the process. So we've got about a 180-degree phase shift, and our loop gain, controller times process, is 1, which is great. So we've got that figure. So let's go back to the lecture, the slides again. If I can go back, I'll stop sharing. Stop sharing. So I'm just going to stop sharing here. Chippy, okay, sorry. Stop sharing. Okay, let me just go. Okay, there, stop sharing. Okay, can you put the slides back again to that one we had before, Chippy?
They are uploading, Steve. Just a
Thanks, sorry
moment,
about that. We're just
please.
jumping around. Sorry to jump around like this, everyone. I just wanted to show you in our labs how the controller works. I just want to give you that feeling for that. I know time is very tight, so we'll quickly move on. Sorry to be so disruptive today, Chippy. Bit of a pest.
Just a moment, Steve. They are uploading. There we go. I'm just going to
Brilliant,
move
thanks.
them quickly.
Different countries. Thanks so much, Chippy. Thanks, everyone, for
Thank you,
tuning in
Steve.
here and listening in. Okay, so we've spoken about the reason for tuning. We've looked at the Ziegler-Nichols. And there we go. Okay, thanks. So this is where we've had the process P times the process gains. We've got a gain of about 1, and of course 180-degree phase shift. So that's why the output has that constant cycling, and that's the Ziegler-Nichols model. So if you go to the next slide, Chippy, thanks. Okay, so the approach to follow with a continuous cycling method, which, as I said, you do not do on your plant, but this is the theory, which you can do with our labs, because you won't break anything. But if you start cycling a plant, you'll do bad things. So I do not recommend this. You put the controller into P control only, automatic mode, make it change the set point, and eventually you'll see continuous cycling. And then you work out your tuning constants. So you may say, okay, what are the tuning constants? So if you go to the tuning constants, next slide, please, Chippy. Okay, so here are the tuning constants. So what we do is we take Kc equals 0.5 times Ku. So Ku was that figure that I showed you on the controller of about 9. So 0.5 times 9 means that we'll put 4.5 in the controller. For PI control, we take 0.45 times Ku, which is the figure which 9, so 0.45. And then the T integral is PU over 1.2. Now, PU, you may say, what the hell is that? PU is the actual period of the oscillation. So if the oscillation, say, has a period of 1 minute, 60 seconds, 1 minute, you divide by 1.2 and you'll say, oh, it's 0.8 T integral. And then if you're using PID control, you will put in Kc is 0.6, T int is PU over 2, which is your period, 1 minute divided by 2, which is half a minute, and T derivative is PU 1 minute divided by 8, which gives you 1/8 of a minute. So you put those in. So it depends whether you use PI or PID control. Now, where do you use PI control? You'll typically use it for a flow loop, because it's got a very quick feedback. If you're doing PID control, it'll typically be a temperature loop, okay? Because there's a significant delay in the loop. So let's move on, Chippy, to the next slide. So this is what you call a first order lag. Can you see that curve, that exponential curve? First order lag. Next slide. And these are different time constants, response curves. So you can see, for example, curve F has a 10-minute lag. And you see the 10 minutes, and it's when it gets to 63%. E to the minus 1. E to the minus 1 is 63%. So basically it gets to 63%. We say that's the time constant. Okay, next slide. Cascade control. So now I know time's run out, we've run out of time, but let's look at cascade control. Next slide. Okay, so here's a particular scenario, single loop temperature control. Can you see that we've got on the left, we've got an inlet with a temperature measurement. We've got T2 on the outlet, and then we've got a combustion chamber, and we're heating up this liquid in a pipe. Very straightforward. We've got air coming in and fuel. So this loop actually measures the temperature T2, and that's the process variable. We then control the fuel. So in other words, if the temperature, you want a temperature of, say, 200 degrees, and your set point's 250 degrees, you'll get an error. You'll drive this output to give more fuel, so you raise the temperature. So this is a classical feedback loop. So if the temperature goes to 300 degrees and your set point's 250, you will then send a signal to reduce the amount of fuel being burnt in here. But the problem with this strategy, is that the flow may come in there, but the actual flow may vary because the pressure, inlet pressure changes, which means you have different levels of flow, even though you've got the same setting of your valve. So there may be a more sophisticated way of doing this, which is also to monitor the actual flow. So we have what we call a cascade controller. So if you go to the next slide, Jeppy. And here is a cascade controller. Can you all see that in its glory? You'll see still you've got no measurement on the T1, but you've got T2. You're measuring that. You've got a controller there. And it feeds the output from the TC, the temperature controller, feeds into the set point of the flow controller. Feeds into the flow controller, and there you are monitoring that. And of course, the flow controller, you're actually looking at the output. But what we've done here is that we're also monitoring the fuel flow with air. So the air actually, we've got control happening right down at the fuel controller level as well. So this gives you far better control. But the challenge with this setup, and that is why many plants have their cascade controllers all in manual control, because you lose your output and your set point aren't always set correctly. And of course, it gets too hard, and eventually they put everything into manual control. Just leave it as it is, and that's all we do. But obviously, we would like a more sophisticated approach. So we got this two controller basic cascade control. Okay, next slide, Chippy. So with cascade controller, your secondary controller, as we call it, is the flow controller, and the primary controller is generally the PID controller, and you've got to make sure it's stable. And with the cascade control, you can keep your gain to less than 1 because there's a flow controller. There's generally very little chance of any instability with this. Okay, next slide. So cascade control, there's a whole tuning methodology there, which we don't have the time to do here. But before we close the session, I just want to talk about public enemy number 1. Public enemy number 1 for PID control, and that's where it destroys the PID controller. And that is when you have a long process dead time. And that is where PID control says, sorry, baby, can't do it, can't hack it. My algorithm is not going to work. What do I mean by long process dead time? And that's what I'd like to look at. Next slide, please, Chippy. So when you have a long dead time, the particular problem is if you have 20% of the total time for the process variable to settle to the new value. And where would this happen? If I can get to the next slide, Chippy. Okay, here, can you all see this particular manufactured problem? And you see that you've got your conveyor belt, got a mass meter there, and we've got a bin on the conveyor belt feeding onto the conveyor belt. But from the time it drops onto the belt, the ore drops onto the belt, to the time it's measured on the mass meter, the process variables, the mass meter, there's a delay. If that delay is too long, your PID controller says, sorry, baby, I can't work. So obviously the idea with this controller is to move the mass meter as close as possible to the actual where it deposits on the ore deposits onto the belt. So that's critical. But if you can't do that, you've got a problem. And this is where the PID controller doesn't work very well. And this is where we actually ideally create a process model, which is called a Smith predictor, which is basically a process model of the conveyor belt. And basically what you do is you still have your PID controller, but you cut out the delay. And we don't have the time to do that today, but you cut out the delay in the PID controller, and it allows just to look at the dynamics. So PID controllers work very well with dynamics. As soon as there's significant delay, there's a problem. So that's where we have to have alternative strategies in place. And that's where we create a process model of that, what we call transportation lag. And we split out the time delay, and we split out the actual dynamics of the process. And dynamics are the ore falling onto the belt, the type of ore, the stickiness of the ore, the process issues relating to the ore. That's what we look at. Okay, so bear in mind, if there's a significant dead time, you've got to look for alternative strategies for your PID controller. You may use a very slow acting PID controller, which is a solution, doesn't respond very quickly. That's one way of dealing with the problem, but you may need to look for a process model, or if you're very good, say, hey, I'm not prepared to put the mass meter there. I'm going to move the mass meter right below the feeder so that I can have no delay at all. That's obviously the best solution if possible. Okay, Chippy, next slide. So we put the easy solution, detune the controller, slow response rate, and take it from there. So just watch out for integral mode, very sensitive to dead time, because integral mode looks at the error. If there's a significant error, it ramps up the output from the controller, and obviously that's not a good thing. So you need to make sure it doesn't ramp it up, it only responds very slowly. Okay, next slide. So in essence, the wrap up is, thank you very much for attending this session. I just want to again tell you that the PID controller is the finest solution for control in a plant. It's the simplest. You've got 3 parameters, PID, and in this, I've hopefully given you an idea of the actual theory behind the whole controller, how it operates. Okay, so thank you very much. Thank you very much, Sheppy, for masterminding this. I'm sorry we had some initial problems. We can blame Microsoft, or perhaps we can't blame Microsoft. We can blame me. Any final comments?
Thank
Thanks,
you very
Chippy.
much. Thank you very much, Steve. I do believe this is the time that our participants can actually put down their questions and either the chat box or the Q&A function over there. However, up on your screen are the courses that we have on offer at the Engineering College of Science and Technology. We have 2 intake dates since we offer 4 programs rather, 2 bachelor's programs, Bachelor's of Engineering Honors Masters in Industrial Automation as well as the Bachelor of Engineering in Electrical Engineering. Those start on the 15th of February and applications are still open. Please make sure to submit your applications. However, if you have questions regarding this or you would like to speak to a course advisor, I'll be sure to leave the links for you guys in the chat box as well as our contact information in case you'd like to reach out. For the Masters of Science in Power Systems, Analysis and Renewable Integration, the date to start is the 9th of February 2026, as well as the Masters of Science in Industrial Automation and Instrumentation Control. As I've mentioned, applications are open for those as well. Please make sure to submit your application in time, and we will have someone get back to you should you inquire and you'd like further information regarding the programs we have on offer. Steve, I see that we have two questions, one from Mark and another one from Micello. Please answer those questions while I move on to the certificate of attendance. Ladies and gentlemen, this is the certificate of attendance QR code as well as link. I'll be sure to leave the link in the chat box as well as our contact information. Please note that you will need to submit the form on time so that you are able to receive your certificate. And as I've mentioned in the beginning, please make sure that you fill in your names as you'd like them to appear on the certificate so that there are no errors. And Jihad is asking, is this online or offline courses? So you can study online with us at the Engineering College of Technology. The programs that we have on offer can be studied from wherever you are in the world. So you can definitely study online with us. I do believe the remainder of the questions are for you, Steve. Whilst you answer, I will be sure to leave the link for our participants.
Thanks so much, Chippy. Really appreciate it. So, got some interesting questions there. Why would you use cascade control? Well, cascade control theoretically gives you better control. So that example I gave you of the heater temperature measurement, basically you're basically monitoring two inputs. You're monitoring the temperature and the flow. So it's a no-brainer that you've got far better control when you've got two inputs rather than one. So you've got a two-dimensional thing. But the problem that you've got is that if your controller, your temperature controller with the output isn't set up correctly, it will drive the flow controller into a bad place, which means that you'll get a lot of instability in your process. So that's why a lot of people, operators say, mate, it doesn't work. I'll just put it all into manual. I won't be using control at all. So that's the challenge. So that's really important. It gives you better control if it's set up correctly. What is the full meaning of PID? It means proportional integral derivative. It's basically, unfortunately, I can't write on the screen, but basically means take the error between your set point and your process variable, multiply it by a number, that's proportional. Integral says take the error, add it up over a short period of time, get an output from that. And the third one is derivative. It says look at the change in the error. Is the error going up or down? And multiply it by a number. Basically, that's what you're doing. Continuous cycling, definitely not recommended in live industrial process. Do not do continuous cycling. You will actually, what you have is damped cycling, which basically means that you make the changes, but your output goes up, your process variable goes up, and then it settles down nicely. It doesn't cycle like that. You do not want to do that. And thanks, Richard, for your proportional derivative comment there. These, what are the real applications? Ziegler-Nichols. It's Ziegler-Nichols is basically just to give you an idea of the concept. What you use is a damped version of that, which basically means you never get to the gain of 9, which I was showing on the controller. You get to a value of, say, 4 or 5, and then you do your calculations from that. And that'll be a topic for another day. I will certainly give you the presentation on that. So control is useful in the process control world, controlling flow, pressure, temperature, whatever. So there you go. How do you distinguish between a first order process? Just look at the actual change in the process variable. That's what you'll be looking at, and put it through your put it through an AI. Put the data through an AI process, and then to say, hey, what is this first order? Is basically the one we use most of the time. It's an exponential curve. Okay, so thank you very, very much for those awkward, difficult questions. Really impressive. Thank you very much. You guys are obviously very thinking. You probably know a lot more than I do, so thank you very much. I've worked, there's some really interesting problems I've had with process control systems, which I'm going to talk about in another presentation. One of them was, which really caught me, was an aliasing problem, but we'll talk about it another presentation. Thank you to Shumbu, James Magala. Very kind of you. Thanks, Abdul Shalom. Thank you very much for your kind comments. Please, I will be back again to do another presentation on this topic. It's something very close to my heart. Thank you, Cheppy. Happy days and all the best. Hope you have a good evening, good morning in South Africa. And I'm going home now. I'm going to be running home in the next 8 minutes.
Thank you so much,
thank you so
Steve.
much. Thank you, everyone. Very much appreciate. Sorry about the problems in the beginning. Please blame me. Don't blame anyone else. Thank you very much. And Chippy, we need to make sure I can write on the board next time.
I will be sure to speak to Tip about that, Steve.
However,
for
thank you very
for our participants, please note that I've left all the links, including the certificate link. They've been pinned up in the chat box should you want to request for a certificate of attendance. If you'd like to interact with Steve again, he will be with us on the 17th of December. He has another webinar, so please make sure to go to the website and you can register for that webinar. We also have 2 more webinars for you guys, so this is going to be a jam-packed week for webinars for the Engineering College of Technology. Please make sure to register. And as I've mentioned, the links are on there. Thank you so much for attending, everyone. See you on Wednesday, Thursday, and see you on Wednesday and Thursday. Thank you so much, everyone, and have a lovely day. Bye-bye.
Thank you very much, Chippy. Cheers. Adios.